Alright, let's start off this video with the challenge problem from the last video. So the easiest acceleration to find will be point y, because we can imagine this as the bottom half of a larger circle. We know that our acceleration is going to be a centripetal acceleration. So to find that, we just start at the edge of the circle and go towards the center. So that will give us an upward acceleration ruling out A and B. Now we have a 50-50 chance. Alright, so your first impression is probably to use the same process for point Z, and then you would get C as the answer. But read the problem carefully, seeing that this ball is going to begin at rest at point X. Now, that means when it gets to point Z, it's also going to be at rest again. And you'll be able to verify this when we get to energy by the conservation of energy. But for now, you should be able to follow your intuition. Hopefully, if you kind of imagine a ball, or you can use it like a pendulum, but if you release it at rest, it should end at rest and change directions at about that opposite point, if you were to mirror it through the center. So because this ball is going to be at rest at point Z like it was at point X, there's not going to be any centripetal acceleration because it's not going to be moving. However, it's going to swing back due to gravity pulling it downward. So that means that the acceleration at point Z is downward, meaning point D is the correct answer. In this video, we're going to be covering centripetal forces. And we kind of touched on that a little bit in the last video about centripetal acceleration. But a centripetal force is like centripetal acceleration, though instead of acceleration, it's a center-seeking force. For example, say you were spinning an object above your head, and this is the view from above, and let's say that object is on a string. Just imagine that to be a perfect circle. The centripetal force would be the tension in the string, because that is what is keeping that ball moving in a circular motion. Or maybe this is the sun, this is a planet. That centripetal force would be the force of gravity. And that is just one of many examples. Friction can also be a centripetal force. Say if you had a turntable, friction is what is allowing that object to move in a circular motion. You can also think about a car rounding a curve. This is just a section of that circle, but just try to imagine that car doing that same curve on ice. It would not be possible because you need that friction to allow that car to turn and accelerate as it changes directions. Alright, like with centripetal acceleration, there's also an equation for centripetal force. You can actually derive it from Newton's second law, F equals ma. Alright, but instead you add your subscripts for centripetal. So that makes centripetal force equal to mass times centripetal acceleration, which we know is v squared over r. Right, so you see, it's not a very difficult question to get if you ever forget it, as long as you remember what centripetal acceleration is equal to. Alright, here is our first practice problem. So we have a car traveling over some hills with a speed v and the radii of those hills being r, if you were to imagine them as just part of a larger circle, and we want to know where the driver will feel weightless. Alright, first let's try to deduce whether it'll be at the top or the bottom of a hill, giving us about a 50-50 chance of getting the right answer. So let's just draw this to be the top of a hill and this to be the bottom of a hill. So at the top of a hill, we can have a sum of our centripetal forces to equal, let's call inward positive. So inward to the circle will have gravity, and outward we have the normal force. Now let's sum the forces at the bottom of a hill. Right, so inward we'll have the force of the normal force, and then outward we'll have the force of gravity. Now this car is having a constant, or well, you could say the same speed at the top and bottom of the hills. So because we know that force centripetal equals mv squared over r, none of those variables are changing, so the sum of the centripetal forces have to be the same at the top and the bottom of the hill. So in that case, the driver is going to feel heavier at the bottom because the weight that he experiences or she experiences is due to the normal force at the bottom. And that normal force has gravity being subtracted from it, so to equal the centripetal force at the top, it's going to be much larger. At the top, we could say this normal force, let's say it equals 0. Then at the bottom, it has to equal 2g, because then the centripetal force at the top and the bottom of the hill will be exactly g. The normal force at the top of the hill could be larger, but that just shows you why how the driver is going to feel heavier at the bottom of the hill. So in that case, I'm going to get rid of the scratch work here. That means we can get rid of B and C, leaving us with A or D. So we're going to sum our forces for the top. We're going to have G minus Fn equals mv squared over r. Alright, the driver is going to feel weightless when there's no normal force. So if that doesn't immediately make sense to you, that normal force is giving the weight that the driver experiences. If that goes to 0, then there's only gravity acting as a centripetal force, and when there's only gravity, you feel like you're in free fall, and therefore you feel weightless. So this is going to drop out, and we know that the force of gravity equals mg, so we have mg equals mv squared over r. We've got m cancel, and then we've got that v equals the square root of g times r. Alright, so there's no square root in option A, but then what's with the inequality in D? Well, this v here is the minimum speed required for the driver to feel weightless. Any speed greater than that and the driver will absolutely feel weightless, and that's why we have an inequality there. So that makes D the correct answer. Alright, here's our next problem. We've got a mass m in uniform circular motion with a radius r, speed v, and tension T. What would the tension be to maintain uniform circular motion if m, r, and v were all doubled? Uniform circular motion just means that an object is moving in a circle with a constant speed. So we can identify tension as our centripetal force. So in that case, tension equals mv squared over r. And now we are just doubling everything. So we get 2m times 2v squared divided by 2r. Alright, so these 2's cancel, and we get m, and then we take 2 squared to get 4, and then we're left with v squared over r. And I'm going to call this t naught. So in that case, t prime, we can just take this and we will get 4 t naught. Oh, and excuse me, these should all be t's, not f's. Though tension is our centripetal force, and we are left with 4 t naught, so choice C. Alright, we've got a ball of mass m attached to a string traveling in a vertical circle, and we want to know the difference in the tension between the highest and lowest points of the circle. Alright, this will be at the top. Let's sum our centripetal forces acting at the top, calling inward positive. So in this case, both tension and the force of gravity act inwards, and that equals mv squared over r, and we'll call this sub t for top. In that case, t sub t equals mv squared over r minus mg. Now we can sum the forces acting on the bottom. So tension also acts upward at the bottom, or inward, I should say. This time gravity is acting outwards from the center of the circle. But this still equals mv squared over r. Nice. In this case, then t sub b is going to equal mv squared over r plus mg. Alright, now we can appreciate our different values for tension. So notice that, like with the top of the hill in the previous problem, or a couple problems ago, at the top of the circle, tension can be less than it is at the bottom of the hill because gravity acts with the centripetal force to keep it constant. However, at the bottom of the hill, where gravity acts outside the circle, the tension force must be greater, like I demonstrated with the 2g versus g. So we want to know the difference between the highest and lowest points for the value of tension. So because tension at the bottom is greater, we're going to do t sub b minus t sub t equals mv squared over r plus mg minus mv squared over r minus mg, and that will give mv squared over r plus mg. Distribute our negative sign, we'll get negative mv squared over r plus mg. So those values cancel, and then mg plus mg gives 2mg, which is our choice B. Alright, here's the challenge problem to this video. The solution will be at the beginning of the next video, or you can find it on my Instagram page shortly after the release of this video.